Alright, this is the part 1 of my screencast for chapters 1 and 2 for the first week here. Just going to go through the table of contents and move on. First of all, this first chapter is very useful for the instrument project. This is a link to the PDF of the assignment, talking about deadlines and the expectations and all that kind of stuff. So chapter 1 is good for that. Okay, so we're talking about waves. Let's take a look at a transverse wave here. We've got a wave being excited by a red dot. And it sure looks like something is moving from left to right, but really all that's happening is every part of the string is just moving up and down, just like the red dot is. Here we have a sound wave. So here, again, we have an excitation on the left, pushing. These are little black dots. Are supposed to be representative samples of the air molecules. I colored one of them blue so you can really see what's going on. You can see that the blue one is just moving back and forth and back and forth. That's really all any of them are doing. And yet there's this illusion of something moving from left to right. So we have walk like that. Okay. So these are the waves we're talking about. What's interesting about waves compared to particles is they can just pass right through each other. In the middle, it seems very complicated and weird, but it's really just their additive sum. And once they're passed through each other, they go about their merry way. Whereas particles, of course, don't do that. If particles were to smack into each other, well, they'd be smacked into each other. They wouldn't keep going. So a cute little movie of that right here. We've got two little blobs passing through each other. The gray is showing what each individual is doing, and you can see that the blue is their additive sum, and then they're just bouncing back and forth and back and forth. Reflection is how you get two waves to bounce back and forth, of course, and so we have string reflection here. Again, the red dot is a representative sample. Let's look at this point right here. It's a fixed point, not allowed to move at all. So everybody else is being pulled, like let's talk about this red dot. He's being pulled up, 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 and then being pulled down, 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 down. Well, let's talk about what this spot is doing. It's about to be pulled down, 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 but it says, no, I'm not going to pull down, so it provides a restoring force, which then gets carried away to everybody else. He essentially pulls up and says, oh, let's pull up, and so they all get pulling up. And so you can get this inversion, which is what happens. Let's take a look at how it works for sound waves. For sound waves, here we have an open end. You see how these particles are able to go way out to the right? So it's an open end. They're not contained. So we have this little pulse that's going through. It's high density, crunched in the front, and then low density in the back. Because you see just behind the crunch, there's sort of a spread out. So heading in, crunch is in the front. As it reflects, notice that crunch is in the back, so it gets inverted. Let's see here. So standing waves. Standing waves are very important for quantum and for all kinds of things. How do you get standing waves? Well, here's an example. Here I have a red wave moving to the right, a blue wave moving to the left, and there's some in black on the bottom. And they both have the same wavelength, they both have the same amplitude. And it's clear that the red and blue give the illusions of moving left and right, but the black one gives no illusion. It's just kind of wiggling. It's not moving at all. That's why it's called a standing wave. This black dot is not moving at all. It's a node, and it's because the red wave is saying move up right when the blue wave is saying move down. So it's absolutely canceled. What does a sound standing wave look like? Well, it looks like this. You can ignore the stuff on the bottom, but here, right here, right about there is a crunch, crunch, open, crunch, open, crunch, open. So the pressure is drastically changing. High pressure, low pressure, high pressure, low pressure, high pressure. And that's what a standing wave looks like inside of musical instruments, for example. Let's go back to this one for a second. It's important to understand that the distance between here and the next place that's not moving here is just half a wavelength. So the distance between nodes is just half of a wavelength. So this picture here has 1, 2, 3, 4, 5, 6 nodes, which means there's 1, 2, 3, 4, 5 half wavelengths in this particular standing wave. So here's some more from hyperphysics on standing waves. I just want to move down. What I really care about is this, showing the different harmonics that you can get. You can get half a wavelength, or 2 halves, or 3 halves, or 4 halves, or 5 halves, or 6 halves. And so these are the different harmonics that you can get from a musical instrument, from a stringed instrument. What does it look like for an air column? Well, let's just scroll right down to it here. You can get half a wavelength, or a full wavelength, or 3 halves, or 4 halves, or 5 halves. The pictures look very similar. It's just different what's happening on the end here. Okay, so if the two ends are the same, either open open or closed closed or clamped clamped for a string, then you get this equation right here. The frequency is the speed of the wave divided by 2L, and then all the harmonics are just multiples of that. So you would stick this extra n in there. Let's see if they've got... Oh, here's what it looks like in an error column, by the way. This is a nice snapshot of that. So normally you would put a little n up here. So F1 is with a 1 in the numerator, but F2, F3, F4, you put a 2, a 3, and a 4 in the numerator here. All right. There's this nice Fourier series applet, which helps you understand the Fourier theorem a little bit better. I'm not going to go to it for the moment. The big deal here is that any repeating wave, anything that can fit on a string, and shape the string any way you want, can really be made up of a bunch of sine waves. This is the so-called Fourier theorem. This is so important because you can just study sine waves, and once you understand everything about sine waves, you've in principle got the tools you need to understand everything. So I would encourage you to play with that applet there. So let's go on to resonance here. So you've got these strings, and they have a frequency they like. So here's a string that it's fixed at this end. It's kind of fixed at this end. It's this red bead that I'm moving up and down. Here I'm exciting it at its fundamental frequency, and so you see I'm giving it energy. Right when it's ready to come back to get more energy, it goes, and then more energy, and it gets bigger and bigger. Here I wiggle it twice as fast, and look, sure enough, it grows and grows and grows and grows. Okay, here I wiggle it 3 times as fast, and here I wiggle it 4 times as fast. Now, okay, so that's how resonance works, but what happens if you excite it at a different frequency, one that's not in the list? Well, here's an example. You can see the string does respond. It kind of starts to move. The big deal here is it doesn't grow and grow and grow. So that frequency doesn't experience what we would call gain or amplification. Here's another example, a slightly higher frequency. The string's definitely moving, but it never grows like, say, this one does. Watch it again. It gets bigger and bigger and bigger and bigger. Here I'm exciting. Look how crazy this red dot is moving. It's kind of a combination of 2 different frequencies. One of them is a resonant one. The other one is not. What the string does is acts like a filter. It says, oh, just give me the one that I really like. This is how musical instruments work. You excite it with all kinds of crazy stuff, anything you can throw at it, and it says, oh, thank you, I'll take the one that I like. And then it amplifies that, and that's why musical instruments sound like such nice pure tones. Here's how a violin works. I'll let you look at that. It's actually pretty cool, the sticking and slipping motion of violins. You can look at that on your own. Here's a closed open instrument, say like a clarinet. You can see resonance happen as we're getting this crunch is getting more severe and more severe. And that's what's going on in musical instruments, of course, on a very rapid time scale. I'm going to stop here and do a different screencast for Chapter 2.